Hello everyone, welcome to another lecture of CS250P, Computer Systems Architecture. For the next few upcoming lectures, I'll be going into details about the designs of modern processors aimed at achieving desirable features such as performance and power efficiency and whatnot. But before we go there, I'd like to spend a little bit of time talking about the design constraints that these modern designs need to be optimized against because pretty much every single um, design decision is a reaction to a particular constraint given to us by physics or cost and whatnot. Okay, the first question I'd like to pose is the following. Given X amount of dollars given to you for designing the next generation processor, how would you architect the best processor? And on the way to architecting the quote unquote best processors, there's probably a myriad of questions that you have to answer. Some examples, just randomly ordered, could include things like would you like to have 4 large cores filling up the chip as opposed to 8 smaller cores filling up the chip? Or would you like to have something like 17 pipeline stages against 40 plus pipeline stages? What these mean, what these decisions mean, we'll get into it a bit more detail in the upcoming lectures. More topics which we will cover in the upcoming lectures include things like would you like to have simultaneous multi-threading? Would you like to have a n-way superscalar? How many way superscalars would you want? Or how many execution units do you want per pipeline? All of these topics will be covered in the upcoming lectures. Other questions could include things like how many registers would you want in a register file? And all of and the big question underpinning all of these decisions would be why? Can we reason about these? And the why, the answer to the why in most of these questions, all of these questions I posed here, in fact, involve the constraints involved in processor design. Of course, if I wanted to list an exhaustive list of design constraints involved in processor design, the list could be quite long. But for today, I'm going to focus on 4 main constraints. The first being the chip area constraint, second being the attainable clock speed constraint, third being the instruction level parallelism constraint, and the fourth being Amdahl's law. So first, let's go into the chip area constraint. As we talked about already in some of the previous lectures, mentioned at least, silicon chips are typically manufactured in units of wafers, where each of these little blocks are chips. How large do we want these chips to be depend on, of course, our design. And once these wafers are manufactured, the details of which we probably won't go into in this particular course, we take out each of these dies, place them into these chips. For example, the one that I showed here is one of the older Pentium chips. And since there is a cost involved in manufacturing or etching each of these wafers, trying to use a larger chip invariably results in higher cost. And if you look at some real-world examples of how much cost we're talking about, here's a table I found online comparing the costs of manufacturing a wafer and each of the chips across an array of these technology nodes spanning from something like 16 nanometers all the way up to 5 nanometers on this table. The cost of producing a wafer of silicon chips have been continuously increasing, at least recently, because it is becoming more and more difficult to etch smaller and smaller transistors onto these wafers. And because of this, even though the size of each transistor is becoming smaller and the area die size required to manufacture a equivalent chip becomes smaller because the manufacturing price of each wafer is increasing, the cost of per chip is not, the cost of a comparably sized capability chip is not falling as fast as, I guess, before, which basically means that Moore's law no longer leads to correspondingly cheaper chips per unit cost. And this is a little bit better illustrated in this chart you see on the right, which I also found online, as the x-axis represents the technology nodes spanning from larger nanometer sizes all the way up to 7 nanometer sizes. And you can see, and the y-axis is the cost per 100 million gates. And you see that the cost per unit number of gates has been stagnating for a little while. And considering, and on the left, this is a table of an example standard cell library I showed in one of the previous lectures. Given that each gate has a particular area cost, given a unit budget we're allowed to spend on a chip, gives us a fairly hard bound on how many transistors or how many gates we can actually put on a chip. Basically, larger chips lead to higher cost. A factor that slightly complicates this constraint is an issue of yield. Because when we manufacture chips from a wafer, there is going to be defects scattered across the wafer due to the characteristics of the wafer and silicon manufacturing. And because if we want to create larger chips from the die, for example, if we want to do something like what we see on the right as opposed to what we see on the left, the probabilities of your chip, each chip, having a defect is going to increase. So if we want to create a larger chip from the same technology and the same die size, compared to a smaller chip, trying to manufacture a larger chip is going to result in more of these chips having defects, meaning they must be discarded, which leads to a lower yield. As a result, typically something like, even if you want a 2x chip size, does not linearly lead to 2x cost. It's going to be more expensive than that due to issues such as yield. So one of the decisions that we must make, I guess, as architects is what is the cost performance trade-off sweet spot in terms of how large the chip do we want to build. So that is the first constraint, the constraint of chip area per unit cost. And after considering this first constraint, constraint number one, we observe that the size of our processor may be limited due to the chip area per dollar cost constraint. So the question becomes, how much chip space do we want to pay for? How large a chip do we want to build? Do we want to build a very large chip and charge expensive money for it, or do we want to build a small chip and charge little amount of money for it? So what options would we have given this constraint of getting more, I guess, performance? How fast can we make this one chip go within this size limitations that is given to us? This leads us to the second constraint we're going to talk about, attainable clock speed. In one of the previous lectures on ISAs, I posed a question such as this one. More complex ISA could slow down the clock. The constraint we're going to talk about here deals with the why. Why does more complex ISA slow down the clock? And before going into this, I need to do just a little bit of a circuits recap. Right. Going into circuits recap, I need to go, I guess, way back, considering I'm going to talk about combinational and sequential circuits first, just in case this requires a recap. So when we talk about circuits, there's typically two types. It's categorized into two types. Of course, there's different ways to categorizing circuits, but here we're going to categorize into two types, combinational and sequential circuits. A combinational circuit is like the one illustrated on the top here, where the output of a circuit is a function of current input values. So if there is input going into one end of the circuit, output is going to exclusively depend on that. It does not have memory of previous inputs. It does not have other inputs. the output is going to be purely a function of the inputs, the current inputs, right? As opposed to a sequential circuit, which has memory, so-called state. And the output depends on both the current input and the sequence of past inputs, which would have affected the current stored state, hence the name sequential circuit. So first, a little bit more detail about combinational circuits and what actually constitutes combinational circuits. I mentioned that in terms of combinational circuits, the output of the circuit depends exclusively on the current input. So when we describe a combinational circuit, we just describe it as consisting of an input, an output, and its functional specification. So the actual function which the circuit is computing. So the value of the output depending on the input and how it can be defined. We can describe it using Boolean logic. It is often described using things like Boolean logic, truth tables, and of course hardware description languages like Verilog, which is used to describe how describe which function translates the input to the output. And when we talk about combinational circuits at the undergrad level in logic design classes and whatnot, this is typically what we focus on. But a constraint regarding combinational circuits, which is often only glossed over at the undergrad level logic design courses, is the timing specification of combinational circuits, which becomes one of the more critical constraints of processor design. So the timing constraints needs to describe, given dynamic input into a combinational circuit, how does the output change over time? And in order to talk about this a little bit, here's just a lightning round of some probably more familiar examples of combinational circuits, including multiplexers. A multiplexer has often two or more inputs going into the multiplexer. And based on the control signal S, the output C of the multiplexer is either A or B, depending on the value of C, depending on the value of S. And of course, we can have wider fan-in muxes, which are built hierarchically using a hierarchy of smaller fan-in muxes. In these cases, the control signal S is going to have more bits, and of course, we will have more ports of inputs going into the mux, which will be selected into a single output. So here we see a hierarchical design of a 8-to-1 multiplexer. Some other interesting examples of familiar examples include things like the adder. So on the left here, we see a combinational circuit for a single bit full adder, which takes in three 1-bit inputs, A, B, and carry. And what it's going to do is going to have a single bit output for the sum. And if this resulted in a carry bit, so if the addition overflowed, if we added 1 and 1 together, it overflows into a second bit. That's going to go into the carry bit, as we are most likely aware. And of course, if we want to do more than a single bit addition, as we often want to, for example, if we want to do a 32-bit addition, we can do something like chain 32 of these things together using the carry input and output to have a 32-bit adder. So in this example, we're going to have 32 full adders chained together in a sequence. Okay, those were some familiar examples. Now we go into the timing specifications. The timing specifications of combinational circuits include a few different parameters, but there's really two important things I want to focus on here. The first one is the propagation delay of the combinational circuit, which is one of the prominent characteristics of a particular given combinational circuit. The propagation delay of a combinational circuit, depicted as TPD, is an upper bound on the delay from getting a valid input to having a valid output. So it measures the time between, given a combinational circuit, it measures the time between when a valid input is given. So you see the input exiting the fuzzy stage at this particular point in time into a valid input of 1. It measures the time between when the input becomes valid to when the output becomes valid. It exits the fuzzy stage and into the intended value, I guess, here of 0. Here's another example when the input crosses the fuzzy area again and goes into a valid value of 0. It measures the time PD between that point in time and when the output becomes valid, it crosses the fuzzy stage and goes into the valid value of 1. And this propagation delay practically restricts how fast input can be consumed, because the input should not change until the propagation delay has passed and the output has become stable. Before the propagation delay has been passed and the output becomes stable, the output of the circuit has not been computed yet. So we can only insert the next set of inputs to the combinational circuit if we want, only after the propagation delay of the circuit has been passed, right? Because if we change the input too quickly to the next set of input, the output cannot change in time, which will lead to undesirable features such as, undefined output. So a good circuit would have low propagation delay, which will allow for a faster change of inputs, which will lead to higher performance. So I guess the question as we can ask as designers is, how can we get low propagation delay? We'll get into that as we move through the course. So that was the first constraint, the first specification of combinational circuits. The second combination of timing specification of combinational circuits is the contamination delay. The contamination delay is a lower bound on the delay between when an input changes to the output starting to change. Starting to change meaning it goes out of the valid voltage range and goes into the fuzzy state. So it does not mean output has reached stable value. It only means that it has begun to change, right? So a contamination delay value of a particular circuit guarantees that the output of this combinational circuit will not change within this time frame, regardless of what happens to the input. If at this point in time the input does something wonky, if it changes to a fuzzy value or anything like that, the output of this circuit will at least hold the previous value for the contamination delay amount of time. So these two numbers describe the timing behavior of a combinational circuit. And we'll get into how that plays into clock speed, the processor speed, in a bit. One thing to note about the timing specification of combinational circuit, and I think this is very important, is that the delay is additive. Both propagation delay and the contamination delay values are additive as we add multiple combinational circuits into a chain. So a chain of logic components have additive delay, which means that the so-called depth of the combinational circuits is important, right? And given a combinational circuit which looks like this is a full adder, which we already saw in a few slides back, by the way. The so-called depth of the circuit, which is the length of the chain of these logic components, The so-called critical path defines the longest path through this chain, the deepest depth through these chain of combinational circuits. And the critical path defines the overall propagation delay of a circuit, because even if there are paths through this circuit which are shorter, we really cannot, let's say, for example, we cannot change the input value to this circuit until the longest propagation delay has passed. So in this full adder example, of course, this is going to depend on a little bit on the actual propagation delay of these individual gates, but most likely because the depth, the chain length, which goes through this one XOR, one and one OR, these three gates, is likely the longest path through this circuit from any input to any output. It is likely that the critical path of these three components, the critical path of this full adder, is going to be the additive propagation delay of which adds the propagation delay of the two-input XOR gate, the propagation delay of the two-input AND gate, and the propagation delay of the two-input OR gate. Basically, a longer critical path means that we're going to have to suffer a slower input rate. So that describes the timing characteristics of combinational circuits. So now we move on into sequential circuits which have state and memory. So combinational circuits by themselves are typically not very useful because there's, I guess, limited use to circuits when, the observable behavior, the output only depends on the current input. Sequential logic adds memory to combinational circuits, which we call state elements. And basically, these state elements inside a sequential circuits act as additional input to the internal combinational circuit. So this sequential, if you look at an abstract model of sequential circuits, a sequential circuit consists of a combinational circuit component and state elements. And these state elements provide some more input to the combinational circuits, and part of the output from the combinational circuit turns into input to the state elements to be remembered. Right. The state acts as input to the internal combinational circuit, and the subset of the combinational circuit output is also used to update state. So this is what we see on the left here is a abstract model of sequential circuits consisting of a bunch of memory elements and a internal combinational circuit. A slightly more realistic depiction of sequential circuits consists of scattered distributed state elements interacting with scattered, again, distributed combinational circuit components. And among sequential circuits, the typical category of sequential circuits which we deal with when we talk about computer architecture is so-called synchronous sequential circuits. In a synchronous sequential circuits, all operations are synchronous. All operations, instead of what I kind of alluded to so far, when we have a new set of inputs coming in every time the propagation delay of the circuit is passed, all operations, including all sequential circuit propagation, is aligned to a shared so-called clock signal. And the new set of inputs can only be inserted at clock signal boundaries, which means, first, the speed of the circuit is determined by the delay of, and for a synchronous sequential circuit to be correct, because everything is aligned to clock signal boundaries, the length of a single clock tick needs to be longer than the propagation delay of the critical path, meaning everything inside this synchronous sequential circuit is going to be synchronous to at least the delay of its longest critical path, meaning the speed of the circuit is determined by the delay of its longest critical path, right? And here I'm just repeating what I already said. For correct operation, all paths, basically all potential critical paths through the sequential circuits must be shorter than the clock period. And if any path is longer than the clock period, either the logic needs to be simplified somehow so that the critical path fits inside the clock period, or the clock speed needs to be reduced so that the clock duration, each clock signal is longer than the critical path. If I spend just a little bit more time talking about clocks, all components of a synchronous circuit share a common clock signal. And of course, like I said before, a typically dynamic behavior starting at rising clock edge, as opposed to falling clock edge, although this is just conventions. Different chip designers can choose basically whatever they want. And because clocks are so important and every single thing depends on having access to the same clock, in order to minimize variability of clock signals at each element in the circuit, typically on a chip, a clock signal is propagated via a very high fidelity special set of wires called the clock tree, so that hopefully all clock signals arrive at all parts of the chip at the same time. But I won't go into too much detail about this particular topic today. So as we add state elements into a combinational circuit and we turn it into a sequential circuit, the timing characteristics, the numbers which we use to describe the behavior of this circuit, we get a few more. Because synchronous state elements also add a couple more timing constraints beyond, of course, propagation delay and contamination delay of the internal combinational circuit. The things that are added include the propagation delay of state elements, which describe the time between the rising edge of the clock, because we're talking about synchronous circuits, rising edge of the clock to having a valid output, being emitted from the state element. There's also a new contamination delay of a state element, which basically means the same thing as the contamination delay of combinational circuits, describing that the output of a state element does not change for this amount of time after a clock change. There's two additional newly introduced time behavior characteristics. The first one being the setup time, basically saying that for a particular state element, it takes this amount of time for new input to register inside the state element. So before this current clock edge, the input to this state element needs to have been stable for at least t setup amount of times before this current clock edge. I'm going to have an illustration about this very soon. The final newly introduced timing characteristics is the hold time, which basically says the input to a state element should hold correct data for at least this amount of time after this current clock edge. Again, I'm going to have illustrations about this fairly soon. So these new numbers introduce a new set of constraints. The first of all, the most critical constraint this introduces is the so-called setup time constraint, which the intuition to which means says the processing of this uh, of this circuit must fit in a clock cycle. In more detail, after every rising clock edge, if we add the propagation delay of the, okay, let's say we have a very simple abstract sequential circuit consisting of state element 1, which is the input to the combinational logic, the output of which is stored into state element 2. And the setup time constraint in this situation basically says the propagation delay of state element 1, so the time it takes for the output to become stable for state element 1, propagation delay of state element 2 plus the propagation delay of the combinational circuit plus the setup time of state element 2, which basically says before this next clock period starts, the input to state element 2 needs to be stable for this amount of time. So the addition of these three numbers must be smaller than the clock period. Otherwise, we won't have enough time for either the state element 1 to emit the correct input, or we won't have enough time to actually do the combinational logic, or even if we did, we won't have enough time for the value to be actually registered inside the next state element so that it can be used at the next clock cycle. So all of these, the sum of these three timing behavior numbers needs to be smaller than the clock period. Otherwise, what happens is that we get a so-called timing violation. So we don't get the behavior which we expect. So that's the first constraint, the setup time constraint. The second constraint is so-called hold time constraint, meaning intuition saying processing should not affect the next state too early. So after a rising clock edge, the contamination delay of state element 1 plus the contamination delay of the combinational logic, which describes the sum of which basically describes when the input to the state element 2 is going to change and goes into fuzzy state. This number must be larger than the hold time constraint of state element 2, because the hold time constraint basically says the input to the state element 2 for this state element to behave correctly, the input to state element 2 needs to be stable at least this amount of time after the new clock edge. And if the contamination delay of these two things combined is shorter than the hold time of state element 2, then the input to state element 2 may have changed before the hold time constraint is passed, leading to unpredicted behavior. So these are the two constraints, the two major constraints, two major timing constraints that need to be met by the circuit which we design. Illustrated in a nicer way, the input so given a state element and the clock and an input and an output, basically says that the input to this state element is allowed to be unstable most of the times, but at least before the setup time for the next clock edge, the input needs to be stable. It should not be in the fuzzy state. And after the rising clock edge, for at least the hold time constraint of the state element, the input should again be stable. So this is the intuitive illustration of these two constraints. The real world implications of these two constraints is, well, there's a few, but one of the most visceral one is that these constraints are going to be met by computer-aided design tools, because these constraints need to be met for every single combinational path between every single state element which may be distributed in our design. Every single pipeline register, every single register file register, every single counter, every single queue, everything between everything needs to be verified and uh, massaged sometimes so that these two constraints are met. And the probability space is so high that in the modern age, that I don't think this is feasible to be done by hand. So CAD tools will do it. Given a high-level representation of a function, CAD tools will try to create a physical circuit representation that meets both constraints for all possible combinations of combinational paths between every single state element. And this may be a little bit controversial, but rule of thumb based on my anecdotal experience is that meeting hold time is typically not difficult. Hold time constraint, as a reminder, is that the input to a particular state element should not change too fast. If the input is changing too fast, typically adding a bunch of buffers, which is, sometimes you can easily build one by putting two inverters together. Adding a bunch of buffers can add enough contamination delay to a sequential circuit so that if we want to really meet the hold time. What's more difficult and typically a more critical constraint in building these circuits is meeting the setup time. If you remember, setup time constraint is that basically the computation needs to fit inside a clock period. And if our initial design does not meet the setup time constraint, we need to either somehow construct shorter critical paths, and we're going to talk in later lectures, we're going to talk about some approaches to doing this, or reduce the clock speed. And of course, we want to avoid reducing the clock speed because higher clock speed will lead to higher performance. So the question becomes, given a function we want to implement as sequential circuits, how do we create shorter critical paths for the same function? And we're going to talk about this in detail in the following lectures. Here's a short aside on placement and routing, which is done by CAD tools, in which they place the combinational circuit elements and state elements into the two-dimensional chip area, mapping state elements and combinational circuits to a limited chip space. This is done by CAD tools, and due to the two-dimensional space restrictions of a chip, this may add significant propagation delay to combinational circuits. So if we have a combinational or sequential circuit design, which inherently don't seem to have too much stuff going on in the combinational path, but the CAD tools complain that the combinational path is too long, sometimes that is an artifact of placement and routing optimizations. For example, and this is a very high level, very simplified view and example of a placement and routing optimization. Let's say we have a complex combinational path 1 and 2, both accessing the state element A. And because 1 and 2 are so large and they both access A, the spatial constraints, the two-dimensional spatial constraints, may push the smaller combinational circuit 4, which also accesses A, far from state element A in terms of its location on the two-dimensional chip. Which means even if the combinational path 4 is small and simple, the combinational path from B, which is an input to the combinational path 4, the path from B to A may now be very long, even though there's not a lot of stuff going on there in terms of actual work. This is one example of how the propagation delay of a combinational path may not always one-to-one correspond to the number of gates or the actual amount of work that goes on in there. We're not going to reason about this very much right now because there's typically a whole course dedicated to talking about this, but I put it here as an example to show that these somewhat unintuitive things can happen during CAD tool operations. Of course, there are some rules of thumb we can apply to avoid situations like this from happening. For example, one combinational circuit should not access too many states. It would be better if they were separated into different combinational paths. And other rules of thumb, including things like one state element should not be accessed by too many combinational paths, so on and so on. There are whole courses dedicated to optimizing in this direction, but I just put it here to give you a taste. So given this newly added knowledge on the constraints and timing constraints of combinational and sequential circuits, maybe we can look back to one of the previous questions that was posed in the earlier parts of the class. For example, why are register files small? In RISC-V, we have register files which are 32 element, so 32 slots large. One of the questions is why is this 32? Why not larger? Why not 1024 or more? When we were talking about ISAs, we talked about one reason why we don't have much larger number of register file elements is that if we have more number of elements, we need to encode more bits into the ISA whenever we want to access the register file. That is one constraint which limits the number of elements we can have in a register file. But perhaps a more critical reason why we don't have more registers in the register file is the issue of timing behavior of circuits. Because register files need to be randomly accessible by the instruction, the register file implementation in terms of circuits need to have multiplexers and demultiplexers before and after the register, each register, so that a single instruction, when it wants to write to any of these 32 registers, it can go through a combinational multiplexer and demultiplexer path so that it can be applied within the same clock cycle. And the same goes for reading. And because I mentioned that if we have a larger fan-in mux or a larger fan-out demux, they are constructing using a hierarchical design. And if we have a hierarchy, we have a longer critical path, and which will basically add to the sequential delay, the propagation delay of the register file design, right? Meaning, as we add more register to the register file, the critical path, the depth and the critical path of the multiplexers and demultiplexers will increase, and the propagation delay will also increase with more registers, leading to a slower clock, which we want to avoid. And that's at least one additional critical restriction to having more register files, even though probably having more register files, if we ignore other costs involved with it, having more register files will probably give us at least slightly more performance. Although, if I remember correctly, it was also observed that as register file sizes increased beyond 32, we did see diminishing returns. So at least from the point of view of the RISC-V ISA designers, 32 was apparently a sweet spot, which balances the diminishing returns of the number of slots in the register file and the propagation delay issues of the register file circuit, as well as how many bits need to be encoded inside the ISA to specify which registers inside the register file is being accessed. So 32 apparently was a very sweet spot number which balances out all of these restrictions, which is cool. To give a interesting real-world example, back in 2002, when this was before Denner scaling ended, and single core clock frequency scaling was still going strong, but the size of transistors on the chip were still larger than what we have now, of course, because this now we have 5 nanometers and lower uh, technology nodes as opposed to back in 2002. Having larger transistors meant the propagation delay through each gate was also longer than what we have now. Meaning, if this is the age of the Pentium 4, when the Pentium 4 designs wanted to meet a very high frequency, multi-gigahertz clock speed, the timing restrictions posed by this high clock frequency meant the setup time constraint of this circuit could only tolerate up to 8 inverters in its critical path. So at every clock cycle, the critical path, the depth of the circuit, could be up to 8 inverters. This is such a stringent restriction. We really cannot even fit a single 32-bit adder into this restriction. So a lot of tricks needed to be played to have a working processor design within these such critical restrictions. Things have become a slightly more reasonable now because the transistor sizes have become so small. But this was kind of the peak of having to deal with timing constraints inside processor design. Right. But this means the clock frequency constraints, the clock behavior constraints we've been talking about so far means that, well, that and the fact that it is difficult to fit a lot of logic inside such stringent timing restrictions means there is a limit to reducing the critical path of a combinational circuit, which means that given a particular point in time and given a particular technology node, etc., there is a limit to the clock speed we can push, even before we start considering the end of Dennard scaling, which we talked about in one of the earlier lectures. After Dennard scaling ended, clock speed scaling ended in general, but even before that happened, due to the issues of these timing constraints, there was a pretty hard limit to how far we can push the clock speed. So now we can kind of answer the question why complex ISA slows down the clock. If ISA is complex, and for example, here I show an example where a parameter can be, where the same parameter can be encoded to different positions of the instruction, and where it's encoded depends on a different encoding. This kind of if statements in the decoding logic will introduce at least one additional MUX multiplexer, because the input to the parameter 1 can come from one of two places, so we need at least one 2-to-1 multiplexer to pick which one, which will add to the critical path of the circuit. So if we have an ISA design which is not very clean, very complex, with many if statements, some of which can be embedded into each other in a nested format, you can imagine that we will have a chained hierarchy of multiplexers at the very least, which will add a lot to the critical path, making the clock speed slower. So that is why. So far we've considered two constraints. Constraint number 1, area. Constraint number 2, clock speed. And after considering these two things, we observed that 1, we've talked about this already, the size of our processor may be limited. In addition, the clock speed of our processor will probably be limited. So architectural questions we can ask here is, how do we optimize the ISA and microarchitecture to achieve the best clock speed given the restrictions? Of course, without adding too much chip space usage. And in addition, given the fact that given the situation that the size of the processor is limited and the clock speed of the processor is limited, maybe in order to get more performance, one additional question we can ask is, can we do more work per clock cycle? Because the speed of each clock cycle is apparently limited for us. Which is a good lead to introducing the third constraint involved in processor design, which is instruction level parallelism. So, constraint number 3, instruction level parallelism. Given a sequence of instructions in a single thread, even some instructions in a single sequence can be executed independently or in parallel if the processor has multiple execution units. So here's an example of 3 operations, which could be 3 instructions of 3 arithmetic operations. Here, in this particular example, we see that operation 1 and 2 are independent because the inputs to 1, A and B, are not dependent on anything, partially because operation 1 is the first operation. The inputs to operation 2, C and D, are not the outputs of instruction 1, so operation 1 and 2 are independent, which means that as long as, if our processor, let's say, has 2 adders, then in its hardware, then operation 1 and 2 can potentially be executed in parallel without changing the output of this program. On the other hand, operation 3 depends on the results of operation 1 and 2 because one of the inputs E is output of operation 1 and one of the inputs F is the output of operation 2. And like I mentioned before, if our processor has 2 adders, instruction 1 and 2 can be processed in parallel, potentially giving us higher performance as long as we invest the chip space overhead of having 2 adders. One thing I want to further emphasize here is that instruction level parallelism, or ILP, is about extracting parallelism from a single thread, a single sequence of operations. Having multiple threads is a completely different story. ILP has to do with extracting parallelism from a single thread of operations. And there are many approaches to discovering ILP from a given stream of instructions and exploiting it for higher performance. And this is what a lot of computer architectural topics target, including things like pipelining, superscalar, out of order. All of these things are approaches to exploiting ILP, and we will talk about this in the later lectures. And the existence of ILP is why, so this is the high-level architectural diagram of the Apple M1 processor. This is why there are many ALUs and other execution units, many instances of this, which are provisioned for a single core, even though a single core executes a single thread. Even though a single core executes a single thread, because we expect this processor to be able to identify and extract instruction level parallelism and extract multiple instructions that can be executed at the same time, we are provisioning more than one ALU so that we can operate on more than one instruction at a given time. I also emphasize that these approaches are transparent and also microarchitectural approaches. Microarchitectural meaning that this has no effect on the ISA, and transparent meaning the programmer has, or the compiler, well, sometimes the compiler will know about this for performance optimization purposes, but in principle, the programmer or the compiler does not need to know about the existence of these ILP exploiting microarchitectural approaches. The software and the assembly is written without being aware of these approaches. For example, the fact that there are multiple ALUs in a single pipeline. So this sounds like a good idea. If the processor can extract ILP from a single stream of instructions, then maybe if can we add can we keep adding ALUs forever so that we can trade off chip space for faster single thread performance forever. Unfortunately, uh, so here's a chart from a paper I found, which shows the trend of exploited ILP, at least in the context of Intel processors over the years. And it shows that the instruction level parallelism that is being exploited shows diminishing returns as, at least in recent years, meaning no dramatic recent developments have been put into place, which does, which, played some magic to exploit more ILP. It turns out because later instructions statistically do depend on earlier ones. So as we were adding things like pipelining and superscalar and out of order processing, etc., we were able to exploit more and more ILP, but it seems that there hasn't been a very recent addition which happened to dramatically enable us to exploit more ILP from a single thread program. So we are reaching sort of a diminishing return there. There seems to be a limit. And this is a slide I showed in one of the previous lectures. Now, maybe these numbers mean more than when we first showed it. Real world examples from one of the older Intel i7 processors and from one of the older mobile class ARM processors. Each of these bars showing the cycles per instructions. So if the average number of cycles per instruction is 0.25, for example, with the Intel example, we'll show that we are exploiting 4x amount of ILP across multiple execution units we have on the processor. But in reality, at least in the benchmarks which were run on this processor, the actually existing ILP appears to be much lower than the ideal ILP appears to be much lower than the ideal 4x. So that's kind of what we're dealing with here. So after looking at the three constraints we've seen so far, the size of our processor may be limited, the clock speed scaling may be limited. Now we add the observation that work per clock cycle may also be limited. Although we have some knobs to turn. If we add more chip resources in terms of implementing things like pipelining, more execution units per pipeline, superscalar, if we throw more chip space at each core, we do get more performance per thread, but we do see diminishing returns. So the architectural question becomes, how much chip space do we want to invest in this diminishing return ILP? Because we do want faster single thread performance, but we do want to balance it out. So one additional question we could ask here is, yes, the single thread performance seems to be at least limited or diminishing returns. What if you had more cores? Which leads us to the fourth constraint we're going to talk about today, which is Amdahl's law. Yes, granted that modern processors are often multi-core, and this is very beneficial. On the left, we see the die layout of a more recent Sapphire Rapids Intel processor, which has many cores, as you can see. And this is beneficial for modern machines because modern machines typically are running hundreds and hundreds of threads. So there is oftentimes enough number of threads to occupy the many number of cores we can put on a multi-core processor. So how about if we invest less in ILP so that we don't go too far into the realm of diminishing returns of ILP and simply add more cores like the processor you see here. And To some point, it does make sense. Yes, sure. And that's what a computational structure which takes this to an extreme is, I guess, the GPU, which I hope we'll have time to talk about in one of the later lectures. And of course, we can do this as long as we care less about the speed of any one task. If we care only about the total uh, added throughput of all the tasks that you're running on the processor, and we don't care about the latency of any particular task, then we can afford to go to this extreme. But if we care about the performance of any one single task, even if it is a parallelizable task, then going this extreme may not be a very good idea due to Amdahl's law. The intuition behind Amdahl's law says, given a task, some parts of it are inherently not parallelizable due to dependencies between operations, etc., etc. So given a program where some portion of it is parallelizable and the remainder of it is not parallelizable, the maximum speedup we can get as we add more cores is described by Amdahl's law. The speedup we can get is basically the parallelizable portion divided by the number of processors we can add to the system, plus the remainder, 1 minus parallel, which is the fraction which is non-parallelizable. So if the particular task is completely unparallelizable, then this part will become 0, and even if you had 1,000 processors, the speedup will become basically 1. If our program is embarrassingly parallel, so it is entirely parallelizable, then if we add more threads or processors, we are going to get linear scaling. And if we look at the simulated projection of various different applications, we see that, so on the top here, the green line represents the kind of embarrassingly parallel application task, single task, which is 95% parallelizable. So as we add more processors, the performance increases significantly. But if we look at a program which is 50% parallelizable, which is still pretty decent, even if we add an infinite number of processors, we are only going to eliminate 50% of the program, which means we only get 2x performance even if we had an infinite number of cores, which places a hard limit on the performance improvement we can get. So I guess if we have a program such as this, and we really do need to run this at a fast speed, because we always want fast speed, we do have to make the choice of lesser cores and using those chip resources to implement more ILP. And here, this is just a sort of a numerical analysis on how programs will behave according to different parallelizability characteristics. If you look at real-world applications, the situation is often even worse. So here, I took these figures from a paper which profiled web applications. And some real-world applications do have fairly good scaling. For example, this application on the Amazon S3 service, which I suppose is very near embarrassingly parallel. As we add more processors, the performance did improve significantly. But for the majority of programs which this paper profiled, either the parallelizable portions are relatively low, and even if you add more processors, the Amdahl's law limits the performance improvement per task quite significantly, or sometimes performance even diminishes with more threads, which suggests that for these particular applications, having a smaller number of cores, each of which are faster, would be beneficial because more cores results in actually worse performance, possibly due to other overheads other than Amdahl's law, including things like the overhead of orchestrating parallel operations. Right. So after considering all of these constraints, 1, 2, 3, and 4, we observe that the size of our processor may be limited due to cost per chip space. The clock speed may be limited due to timing and delay issues. Work per clock cycle may be limited because of ILP limitations, and the benefits of more cores may also be limited due to Amdahl's law. But all of these constraints, all of these observations do represent a knob we can turn. If really necessary, we can and if we observe that more chip space does give us good benefits in terms of performance, maybe we are willing to pay more cost. If we can design the ISA in a different way, or if we can architect the microarchitecture in a different way to get us more performance, higher clock speeds, even if you have to sometimes spend more chip space on it in regards to differently architected processors or more pipeline registers, etc., we can turn that knob as well. We can also exploit more ILP if that is beneficial for our particular application. We can turn that knob as well, even if it does give us slightly diminishing returns. Maybe it is not very diminishing for a particular application we care about. We can turn that knob as well. And if the application we care about has good Amdahl's law characteristics, then that is something, that is a knob we can turn as well. For example, how can we balance core count versus ILP given the chip space limitations? And the high-level observation from all of this is that none of these resources, chip resources, clock speed, ILP, and parallelism, none of these scale forever. So we do need to balance all of this somehow. And we cannot actually make any decisions on how we will scale this. For example, just looking at these restrictions, we cannot actually decide how many cores. We cannot pinpoint right now that yes, we want 4 cores, or yes, we want 8 cores at this point in time, without considering the actual characteristics of many things, including technology nodes. But most critically, the decision needs to be driven by the characteristics of the applications we care about and the benchmarks we care about. And that's part of the reason that, for example, if you benchmark the behavior of desktop class i7, i9 core chips versus the server class Xeon chips, they make different uses, they make different trade-offs between things like cache sizes, number of cores, the amount of ILP exploiting functional units, such as caches and prefetch logic, etc. Different decisions are made for these different lines of processors based on these restrictions and observations about the applications that each chip cares about. So that has been the restrictions that modern processors need to abide by when being designed. And next lecture onwards, we will go into details about the tricks, architectural decisions, and other technologies we use to actually turn each of these knobs. And right, thank you, and see you at the next lecture.